In this video I'm going to look at how to calibrate the binding energy scale for survey measurements. The example that I'm going to use are a set of survey measurements that are taken from a sapphire wafer. This is essentially an insulating material, so we do need charge compensation if we want to do this well. A set of survey spectra, and each set are measured using different operating modes. We've either got the flood gun off or the flood gun on in both cases, and one pair represent an electrostatic lens mode, so no magnetic lens is involved in this measurement. This was measured from an Escalab 250XI, and here we have a magnetic lens mode that is designed to improve sensitivity, and once again we've got flood gun off and flood gun on. So I'm going to open these files and we'll see that each file contains a list of survey measurements. These all represent repetitions of the same spectrum measured at the same point. So in principle, if the job was done well, then we ought to see identical spectra that all are showing aluminium peaks here, oxygen and a carbon 1s. These are the principal peaks from the sapphire. The carbon is adventitious. It's not expected to be part of the sample. So this represents a surface layer. And typically the carbon 1s is used to charge correct, meaning to calibrate the binding energy scale. Now the reason that we need to calibrate the energy scale is that the photoemission peaks do not arrive at a specific binding energy. They actually arrive at a consistent energy, and that translates into an apparent binding energy, which requires this adjustment to make the binding energy scale meaningful. Now the precision with which we were going to make this calculation is not that great for survey measurement, so I'm happy to use 285 eV as the position of the peak for the carbon 1s. As you can see here, it's 286.9, 287. So we're going to calculate a shift, and that shift needs to be calculated for each of these survey measurements and applied on a row by row basis. So each survey measurement has potentially a slightly different binding energy calibration, and that will be accommodated by the use of the calibration property page on the spectrum processing dialog window, where I'm going to make use of apply by row first region, and also the true energy has automatically come in as 285. Since I'm going to use a region, I'll also adjust regions as part of this calibration step. That means that the region will move with the data, and the data will all be shifted by the amount calculated to position these carbon 1s peaks all at 285 eV. So let's do that. First of all, create a region. So I place a region around the peak. That's for the sake of completeness, make that C1s, so it reminds us what we have done to calibrate these data in terms of the region. This is carbon 1s. I've now created a region on one of these spectra. They're all selected, so I can now propagate the region to all of the spectra. And there you can see the backgrounds for all of these spectra. I'm also going to tick the button that says Calc Max. So what happens when I select the Calc Max button is that a quadratic will be put through the top of the spectra, and the maximum of that quadratic will be defined as the peak position. So having done so, I can now bring up the spectrum processing dialog window, calibration property page, just verify that everything is exactly as I left it. Only the true value will be used in this calculation because the measured value is going to come from these regions. So if I look at a region, here we have the measured value. That's the measured value for the binding energy that will be used. That's the true value. When I press the button apply by row first region, all selected, I can now do the calculation. If I redisplay the carbon 1s, I get to see that the calibration has been reasonably successful. I can double check that by looking at the value that is offered in the region now. It's 285 with a bit of change, but all of these are now very much at the expected binding edge for our carbon 1s. So once we've done that, we're now able to look at other peaks in the spectrum and attempt to make sense of the binding energies for the aluminium 2s. That's 118.9, and the aluminium 2p, that's 74.3. So these would be the values that we can now read off for the binding energy that's calculated from these data. Performing charge correction or energy calibration is somewhat dependent on how well you do your charge compensation. Not surprising perhaps, but it's worth saying, because it's entirely feasible that you look at a spectrum that's measured, such as this one, which has been measured using the same lens mode with the magnetic lens, and the flood gun is off. We see peaks that all look like the aluminium and the carbon and the oxygen, so we might think, oh, okay, we can just correct these data and that's good enough. So let's see what happens if we do the same operation yet again, but this time observing that the iterations do not produce identical peaks, so they are moving around. Still, we might be able to correct based on the carbon 1s and then achieve a decent calibration. So let's do the same thing again. Let's put a region on, and let's remind ourselves it's carbon 1s, propagate, and then spectrum processing, calibration. We've got the same true value, region selected, and apply by row first region. And when we look at the carbon 1s, it looks like it's worked. We've aligned all of these peaks, so the peak shapes look reasonably good. So how bad could it be? Well, it can be quite bad. Despite having aligned these peaks, you can see that some are not aligned. So the very first measurements that were performed, we do not have a good energy scale. It's non-linear. It's not a constant offset between peaks, because that's what the assumption was, that there would be a constant offset between peaks that we could correct for by the calibration step, and that's just not true. Now let's have a look here and say what was the energy of the aluminium 2s. Well, we know that the first two are definitely wrong. These are starting to look more consistent, so there's some possibility that we've got data here. Let's get rid of these two windows so we can see the energy, and it comes out as 124. So I'm using an average. Maybe if I move a bit further over, 124 still. It's 123.7. That's very different from the 118 that I obtained from the well compensated sample measured using the flood gun. So despite there appearing to be some sort of consistency here, we can certainly say that the energy, the binding energy scale calibrated based on the carbon 1s alone, is not the same as when we've used proper charge compensation. The reason that we've experienced a problem in calibrating these data is that the original data was offset by more than 200 EV by not using the charge compensation, no flood gun. So let's have a look at one that's not quite so bad. This is the electrostatic mode off. Now here we have a shift, and the shift from 0, which is a good reference point, to the where the signal arrives in the data, that's about 37 EV. So that could be somewhere in the region of about 30 EV shift. So that's not 200 EV. but it's still a shift that we must verify is okay if we're going to use it as data where we can read off the binding energy scale. Again, let's go through and add a region, then do exactly the same thing, give it a name, propagate, use the spectrum processing dialog window calibration property page, got the same true, region adjust, and apply by row first. Region, again, very good. Looks like the signal from the carbon 1s has aligned nicely. Let's now pop out and have a look at the aluminium 2s again. That, when we had good charge compensation, was coming out at 118.9. So what do we have now? We have 118.9. So the calibration for this electrostatic mode with the charge compensation off seems to have produced a reasonable calibration, and as you can see, the fact that we didn't have such a big shift has made a difference to the results that we're getting for these peaks. So that peak there, it's about right. So different modes of the same instrument can produce different results with and without the charge compensation. So we have to be very, very careful how we measure samples. It's not that every sample will behave this way. This is a very specific sample where we have layered materials, and that has complicated the whole scenario. If this was a bulk insulating material, then we may not have such problems with charge compensation off. We may actually have worse problems with charge compensation off. It really depends on the sample.